Test. Hello everyone. Is this working? It looks good. Okay, welcome back to the stream. Welcome back to the project. Tonight is gonna be a tiny bit different. First, sorry for not streaming last Thursday. I had not yet established like it was twice a week, but I kind of wanted to stick to twice a week, and I'll try to stick to twice a week moving forward. But last week was weird. If you were not there last Tuesday, on the 1st of April as they were, the stream was kind of derailed last time because while we were writing tests, the test we were working on was a property based test in which we generate a random AST, pretty printed, parse it, pretty printed back, and check that we get the same thing, as in checking that all of those moving parts work correctly. Last time we ran into a case while debugging this where the generated test was saying that the string underscore SE was passed as being the keyword use. And it took me like a long time to figure out why is this happening? And it turns out that the bug was in the least likely place imaginable. It was in Alex, the Lexer tool we're using. Give me one sec to check this. And so it turns out that live on stream last week, we discovered a major bug that had been lurking in Alex for 14 years. So yeah, that was fun. So I guess tonight, before going back to the stream, going back to writing code, finishing the tests, and getting back to what we are doing, I'll talk briefly about what happened because I think this was interesting. Let me just... there we go. So let me show you an example, a smaller example of the bug, because I've managed to replicate it. Last time during the stream, I started duplicating. I duplicated the project that could have a smaller version of the code to try to figure out what was wrong. And I've been working for days on like trying to reduce the bug to the smallest form possible. And the smallest one I arrived at, after I understood what was wrong, so I'm skipping steps here, is this. So here is a small Alex file that, again, there's only two rules here. And what this says is if we match ABC, then the result is the right value ABC. If we match any of the characters A, B, or C, then we use the left constructor. That means that the string ABC should scan as the right ABC, and BBC should scan as left B, left B, left C, because ABC was never matched, and BBB likewise. If we try, however, to call Alex on this file, wait, am I running the fixed version? Yes, I am running the fixed version, so the bug is not showing. One sec. Let me go to Alex and go back to master, which I don't care about the changes in this branch. I'm done working on this at the moment. And oh wait, no, because I think their master now has my fix. So I would like to be on. Where is theirs? Yeah, now is, so I should be before this one. Okay, so this commit will have the bug. What's the overwrite policy equals always, I think? Oh wait, no, I think... Is it because I am running a version of Alex that has the bug with this configuration? No. Yeah, there we go. Okay, no, I don't need to reinstall Alex. The one I have installed does have the bug. So everything I've done on the repo, please ignore it. I thought I've been running my own version of Alex locally to try to debug what was happening. I thought I was running a fixed version. I was not. So here are the two rules again. If we match any of A, B, C, we use the left constructor. If we match ABC in order, and Alex always matches the longest string, return ABC. Here, when we scan BBC, we should be matching. We should never be matching ABC, so we should be returning left B, left B, left C, left C. And as you can see here, we're returning right ABC. Alex gets confused and thinks that this BBC string is in fact ABC. So that is a pretty bad bug, and it was very interesting to figure out what went wrong. So if I run, if I go back to this Alex debug thing, if I run Alex with debug statements on this Lexer file, things become, was it not X minus D? I thought it was. Oh, there we go. If we run with Alex minus D, I get debug information, and we can see here what happens. It all fits on screen, perfect. So here, when we are trying to read BBC, we start in state 0, we go to state 1, state 2, and we accept write ABC, which is not correct. There's another way to get the state, which is, I think it's minus I, which, if I remember correctly, yes, prints a lexer.info, which gives us the list of states. So this here is the list of states that the state machine within Alex will go through. We start in state 0. If we encounter 97, which is character A, we go to state 2. If we encounter 98, we go to state 1. If we encounter 99, we go to state 1. State 1 is just, yeah, we've found a character that we accept. So it's just accept and call the action 0, which is for us just call left. Otherwise, if we have an A, then we go to state 2, which is different because we could accept here, we could finish like passing here, or we could match a B, in which case we go to state 4. And in state 4, if we match a C, then we go to state 3, there we accept with the other action, which is the right, when we match ABC. So Alex will try all branches until nothing matches, and will pick the longest accept. So if we match ABC, we will go through state 2, state 4, state 3, we will match ABC. Otherwise, the longest match will be this one, state 1, or this one, state 3, when we match only the A, but not the B after, and the B and the C after. The thing is, there's a second step to this, because this is correct, which is the minimizer, which is basically we have this large, like, state machine, like, automaton that tries to determine, okay, given the input string, what do we accept? And Alex attempts to minimize a given automaton like this to try to reduce the number of states. And if we look at the reduced version, state 0 on A or B or C, we go to state 1. And state 1 is accept if we don't continue matching, which is the left case that we expect. And if we match a B, go to state 2. If we match a C, go to state 3, and then accept the ABC. The problem is this replicates the bug. If we start with a C, and then we have BC or BBC, we consider it the same as if we had ABC. What happens is this. During the minimizer phase, what the Alex is trying to do is to find states that are equivalent, as in they have the same accept and they are indistinguishable. Like, we can't make a difference with their input. So it's not just that they have the same accept and the same like state transitions. It's also that like everything before them also matches. And here, I think this is one that could be matched. No, I don't think there was anything that can be simplified here. However, here, the code believes that state 2 and state 1 are identical and can be merged. So what's the problem? Let's look at the code. I should be on the correct branch in Alex now. So pre my fix. So here is a big comment that explains Hopcroft's algorithm for DFA minimization. Copy pasted from Wikipedia. That's important. We'll get back to it. And that explains basically this process of we start with sets of ranges, like set of states. Well, sets of states, and here's the algorithm we apply to try to cut those sets of states until we can't cut them anymore, and any set at the end only contains states that are indistinguishable, and therefore that can be merged back together. And there's a function here in Alex's code called group equivalent states that does exactly that. For this kind of state automaton, returns a list of sets of states that are the list of the sets of equivalent states, basically. And the thing is, looking at this code, some of it I dislike a tiny bit from a personal perspective. Like I don't like some of the naming things, but it seems to be fine. But when I run it, I could replicate the bug where at the end, those two states are supposed to be different, are considered the same. The problem was in the comment here. And I don't know if the person who copy-pasted it from Wikipedia got it wrong, or if Wikipedia was wrong. If it's any indication, the French Wikipedia page for the algorithm is slightly wrong. It uses names that are not mentioned. Like it is... I wouldn't call it wrong per se, it's just... it's lacking a bunch of definitions that would make it correct. So it is not impossible that the person who copied this comment from Wikipedia copied correctly something that was wrong on Wikipedia. And the problem is here. The initial sets of the algorithm, where here, starting with Q not containing all of the sets, if you go through the logic of this, means that in some rare cases, some sets will not be properly split, some starting states will not be properly split, meaning that we end up with some states being combined at the end in ways that they shouldn't be. So yeah, this was probably a problem caused by a copy-paste from Wikipedia that has been lurking in the Alex code for 11 years. The patch was basically rewriting this to not use those definitions of P and Q and have instead like reusing the optimization that's here using R and Q, but changing Q to contain all of the states instead of a subset. And it works. So yeah, that was a fun week of trying to replicate a bug in a long-standing project. There's a fun bit, which is there was a patch a year ago that introduced this optimization that's listed here and rewrote some of the code. It has the same problem, but since the code was changed, it's not the same example that makes the bug arise. To get an example that made the bug arise in the pre-optimization version, it was enough to swap those two rules. That made the bug happen again. So my patch contains both tests, this one and this one, to make sure we catch both versions of the code. So yeah, that's why the stream last week was derailed for 2 hours, there was a bug in Alex that had been lurking in the code for 11 years. Fun stuff. Now, with this out of the way, I should probably install my own version of Alex if I want to avoid... Because I don't think if I run the code of the project, it will use a new released version. So I should probably actually just install... So I should get to the current one, and I should just do a cabal install of this version. I think it's overwrite policy equals always that I want. Because at the moment, I think if I do this... Yeah, I'm on an old version. And if I try again, yeah, I get the version. So now we should be able to get back to our project with a correct version of correct version, a up-to-date version of Alex running in the background. Oh wait, no, because we're using Stack, and Stack I think will be trying to run. So I think if we try to run it now, we're gonna have the same problem. I guess what happens. Can I force Stack to use the up-to-date version of Alex? Can I here say 3.5 point whatever the proper version was? 3.5.3.0. Would that work? Nope, that doesn't work. Huh. I don't remember how to specify a specific version for this. That would probably be here. This was 3.5.3.0. Otherwise, we just have to change the rules in our file because, yeah, now I saw. Perfect. Because since it was a matter of how the sets get processed in the minimizer, the order of the rules mattered, which is why it was so hard to find a way to replicate the bug. So in the worst case, if we can't get an up-to-date version of Alex, it will be enough to just reorder the rules in our Lexer file. Okay. And I think I want to run it a few more times just because we had a few weird bugs last time in the round trip. Actually, I'm just going to change one thing. Where is that test again? I don't know how to specify, since I'm using the autocollect thing, I don't know how to specify that I want this test to run more. That's fine. It seems to be running fine, so... So now, where are we? Because of this interrupted the stream last week. Where were we when this happened? When before this whole parenthesis happened? I think we were done with writing the AST. We were trying to write some tests to ensure that the things were working properly. We have some golden tests. We have some. I see a basic test. Yeah, it is just a golden file. We had found some bugs in the AST, we had found some bugs in the Pretty Printer, but I don't remember if there was anything else that we wanted to tackle before moving on. So I'm gonna assume that with this Alex bug figured out, that everything is now fine. And what do we work on today then? Huh. I think I wanted to take a detour. We have two options. Either I start working on the analysis phase. Now we have the AST, start doing the renaming phase, the type checking phase, that kind of stuff, and the lowering into IR. But I think I want to prepare those a tiny bit to have an idea of where I'm going, even if I don't write code outside of the stream, and I have not done that work yet. So I think tonight I'm gonna make progress on. Oh, do I want to do some of the optimizations, like some of the AST rewrites, like constant inlining and so on? No, because that's last. That's after we're done with type checking and with renaming. So no, we're not gonna do that yet. Okay, I guess no. I think doing something a bit of a break and doing something with the bytecode I think could be fun. So I think let's do that. because here is where we're going to be purely in the realm of we're trying to make an image. So basically, we've made the input for all the complicated part of the project, which is the IR and like lowering into IR and optimization, which is the hard part. So we've made the input for this, which is the AST. We are able to pass an AST from a code file. Now let's make the output of this optimization and assembly phase, which is the bytecode, as in something that represents instructions, Piètre instructions, that we can then convert into an image. And this is going to be, so let me open for reference the original Piètre documentation page. There we go. So we're going to want to have one instruction per Piètre instruction. Add, subtract, multiply, divide, mod, not greater, pointer, switch, duplicate, roll in and out. Actually, there's two ins, two outs, so I should probably differentiate them. So in character, out character, and in int, out int. How many instructions is that? At 17, so that's correct. And on top of that, we are gonna want to have bytecode instructions for groups of Piètre instructions that correspond to very specific groups of blocks that we're gonna want to reuse, like pre-made, basically. And those are going to be, if I look, can I open in this actually? If I open the logo, can I zoom in here? Maybe this is not the best way to open an image. Oh, I'm in the wrong folder. If I open this version of the logo, because the logo is itself a Piètre program, as previously mentioned, the way we're going to be organizing our images is basically each vertical strip like this is a function. And the top strip here at the top is an addressing system, which will, like, every time we want to go somewhere, whether it's a go to or a call or return or anything like this, we push on top of the stack the address to which we want to go, and this series of instructions basically like checks, is this less than 2? If yes, like flip this direction, otherwise do -2 and continue. And likewise here for each thing. So this gives us a way to decide, like, given an address, pick the right place. So we're going to want a few specific blocks. One of them is going to be the entrance block, I guess. We're going to want an exit block, which is probably just like the unconditional push an address. That's not, yeah, we could exit, we could jump. Like basically this unconditional, we're leaving the block of this function while pushing an address on top of the unless we consider that the push itself is already part of the thing, and therefore the call is itself just that. And we want one for the branch, basically the branch instruction, where what do we do here? Because I did this a long time ago and I don't remember some of the specifics. I think we don't need anything because it's basically push the address, push the instruction, like push the, like have on top of the stack the address to which we go in case we branch the test. If the test is positive, we actually like just go to the thing, and otherwise we pop it, I suppose. Yeah, I think this is a pop action. Is it a push? What did I do with this? If we look at the colors, this is clearly going from magenta to light green. That's 1, 2, 3 in hue and minus in 2 in light. So that's 3 steps in hue, 2 in 2 darker. That's the switch instruction. Okay, so that's the one that tells us either continue on the left or go to the right. And if we're going to the right, we are doing from light green to dark green, which is 2 darker, which is a pop. Huh. Oh no, it's only 1 darker. No, it's 2 darker. So that is a pop. Interesting. Why are we doing this? Because I thought the switch consumed the value. I don't remember this very thing I did myself. Because then this is from regular red to 1 darker, which is a push, so we're pushing this value here. Is it because this is a return? I genuinely do not remember. Oh, unless it's because... So this transition from purple to light green was the switch. The transition from... Is that dark cyan to magenta? Dark cyan to magenta. So that's 2, 2. Oh, it's a not. But I thought the switch instruction would consume the value. Yeah, switch pops the top value of the stack. I guess the way things were organized, the value here needed to be popped for the address to be there. I guess it was just a manual optimization I had done. I think it's gonna be enough to just have a like this needs to be a switch basically. And then don't do any optimization before that. As in reorder the stack in such a way that like when we switch, we pop the value and we have the address on top, and this branch just has to go. Ah, but what do we put here then? Actually, it's enough to just have the switch and with white on one side, black on the other. Because if we switch, then we exit because we hit the right on the black blocks, we rotate 90 degrees, we exit. Otherwise, we just, yeah. So I think this was a manual optimization that we don't need to replicate. So we need an entrance block. We need an exit block. I guess we want to differentiate return, call, branch, because branch is local, so we don't need to care about return values and the state of the stack as much. Call, we need to maintain the stack probably because this is a function call. And return, likewise, we need to make sure. Actually, return is the easiest. Return is just, we know that whatever is on top of the stack is the address, so return is just the unconditional, we leave the function. Call the address is probably the most interesting. And branch, I think, requires an address as well. Unless, so the thing is, what I want to be able to do at this level of the bytecode is to have the address be the name of a function, basically, rather than an actual hard-coded address, and then do a linker phase, kinda, where we assign a unique number to each address, so that then I replace those numbers in all of the functions, and then we can do this. However, I think it would make a lot more sense for the push of the address to happen. Like, do we have a separate thing for push of an address? Or do we make branch push the address, swap so that it replaces, so that it puts the condition back on top, and then, yeah, I guess it makes more sense like this. So return call branch, that should be enough. And we are gonna need, I think, a special, we're gonna need a special instruction, which is just like the terminate execution, which is this thing here, or whatever form we end up making it, which is just do something where the evaluator cannot exit the current block, which stops the evaluation. Okay. Can I derive traversable and foldable? Probably not. So now the linking phase is going to be, but to do the linking phase, I'm gonna have to know, I should have prepared more in advance. This LX bug has really derailed a lot of things. We're gonna need to figure out name mangling. I guess I don't have to. I think it's enough to just, for now, I can just say that the name of a function is just some piece of text. The actual mangling will be something that happens before, so we can assume that we just already have the names in place, and this is just like matching them, so we don't need to do anything more than that. Okay. So let's work on that. So what is our linking phase going to be? We're going to have a hash map of, I don't want to use identifier here because that's not the correct. I'm going to use a new type that hasn't been introduced yet. I'm going to just call name, which for now is just going to be an alias to text, which is opaque. We can figure that out later. And the name of the content of the hash map is, for each function, we are going to have name of each function, we are going to have instruction. Beg your pardon, 1 second. I need to block a the Twitch interface to report someone is very unintuitive. And last time I accidentally gave mod permission to a bot for a terrifying second. Okay. They should be blocked. Yeah, okay, perfect. Sorry for the interruption. So yeah, we're going to assume we have the name of the functions, which is going to be the mangled name, which we have not decided on yet. But for now, that's just some text. And each function will be containing a big like list of byte code in which the function names. Actually, do we have? I'm missing something, I think. But they're going to be just names. We are going to a place. And actually, they're probably going to be name and int. Because there's one we forgot. Because call is a function call, therefore we need to push things on the stack and we need to maintain some of the... We need to push the return address. That's the thing. There we go. That's why a call is different from a thing. We need to specify the return address and then push the address we're going to. Branch is just local, so it's just an address in the current function. And I think we want a goto as well, which is just an address in the current function. And so as a result, we know that calling a function will always be calling address 0 of that function. But that means... Let me think. Like, do I want the int to be part of this, basically? The question is, do I, ahead of time when I do the assembly, remember how many entry points there are in a given function, or do I do that as part of the linking? And I think I'm going to do that as part of the linking, and that means I will have to differentiate between, like, I think the entrance block needs to have an address as well. No, because it's always going to be just a function name, so it doesn't. But I guess that means a function call will need to contain its own entrance block and therefore will count as part of the numbering scheme of where do we go back. And where do we, therefore we don't need to have the address here where we go. No, actually we, because it's gonna be determined by, it's going to be determined during the linking phase. But we need to know where we're coming back because we need to push the return address. So I guess we need to have the address, and I guess at the input of our linking phase, we just have the function name. Like, yeah, when we call a function, this is the function we go back to, and the actual index within this will be determined during the linking phase. That's fine. And the output of the linking phase is going to be... It's not going to be a hash map name. The names are gone at this point. I guess I need to know the name of the starting function, which is supposed to be main, but, you know, mangled or something like this. So it's going to be, here's the list of all the functions we have, and their bytecode, in which all addressing is done by name. Here's the name of main, basically the starting function, from which we have like to terminate at the end. Like we start there and we're gonna be terminating there. And the output of this is going to be a list of lists of instruction in which we have no longer, the address is no longer a name, but it is a, let's call it a pointer, which is an int. And then it's just a matter of rendering this list of instructions into an image. Okay. So how do we do this? I guess it's just a matter of which of us, each function in the thing, starting with the one that is the main one, and what do we need to keep track of? Basically, the idea of the addressing thing, if we look at this image, is that this will be address 1 or 0, depending on whether we index it by 1 or 0. This is going to be 2, this is going to be 3, this is going to be 4. So we need to finish passing a function to be able, like, finish linking a function to be able to know what the start address of the next one is, which is fine. I guess there's something that's missing here, which is, do we want to handle errors at this point? I don't think we do. As in, I don't think we want to handle errors gracefully, in the sense of this is going to run after we run our own assembly, and we're never gonna run this linking phase on something that we have not generated, which means we can make some assumptions about the shape of the code that we can verify, and we can just like panic if those assertions are wrong, because we are not depending on some user input. We're depending on the output of the assembly phase where we have generated the bytecode from the IR. So I think we can safely make assumptions about the shape of the bytecode there. For instance, we can make the assumption that every function starts with the entrance bytecode instruction. Or do we just decide that there's no need for the entrance bytecode instruction and it's automatically inserted wherever needed? We could make that case, actually. Like, I might not need to have an entrance, I can just... Or do I add it as part of this phase? Do we reuse trees that grow to prune the branch entrance as part of the output? Because where are we gonna need... No, I think we can't know that. Because we need an entrance at the beginning of every function. We need an entrance after every call or return, unless it's the last one, I guess. Yeah, I think it's easier to just let the assembly phase dictate whenever we need one and just trust it, basically. Okay, so we are gonna need, what are we gonna need? We have our functions, we have our main one. I think we're just gonna want to have a state monad in which we keep track of the current index, because that way we will be able to keep track of, like, okay, for each function, where does it start? Ah, we have a complication. Ah, this is going to be interesting. The question is, how do I want to handle this? Functions can be mutually recursive. A function A can call a function B, which calls a function A back. That's fine. That's allowed. The problem stems from the fact that, like, okay, to know where a call goes, I need to know. So if I'm processing A before B, to know where the call to B, the address of the call to B is, I would need to have finished processing A to then be able to do the lookup in the hash map. I guess if I use a lazy state, I can probably do that and have basically each function do the lookup in the hash map. That's going to be constructed as part of this process, and as long as nothing is evaluated ahead of time, that should be fine. That should be fine, yeah. So we just need, I think, to label all of the addresses as lazy, because I have strict data on by default. And here I think I need to import control monad state lazy explicitly. Okay, yes. So I started the stream with this. I did file the bug for Alex. and I could not let it just like, I couldn't wait. So I started debugging the thing. So I spent 3 days basically nonstop. I didn't sleep much, and I forgot to stream on Thursday, finding smaller and smaller like repro cases to be able to isolate the bug, introspecting the internals of Alex. I found the bug, I patched it. The new version of Alex has been released with my patch with the bug fixed. It has been quite an interesting week. When I came back to this stream, I had no idea where we had left the project because I was completely sidetracked by this whole Alex thing. But yeah, there was a bug in the optimizer of Alex that had been in the code for 11 years and which stemmed in all likelihood from a mistake in some pseudocode in the description of an algorithm on Wikipedia, which is quite something. The gist of this is basically I was explaining this earlier in the stream. Do I still have it here? Basically, Alex under the hood is using a state machine. Wait, I had it earlier. Let me go back to here. Actually, no, I've installed a fixed version of Alex, so we might not be able to see it. Yeah, I've installed a fixed version of Alex. So if I run, oh wait, the info file might still be from earlier. Yes, okay, so I can show you this. Here's a set of two rules. One which is when we match either A or B or C, we apply the left constructor, and the other one which states when we match A, then B, then C, we apply the right constructor because we have matched the string ABC. And of course, since Alex matches the longest string, whenever ABC appears, we should be getting ABC. When we get A, B, C separately, we should be getting them like segmented. If I go back to... If I go back... to before my patch, basically. And I install Alex with this. I don't have it anymore. Oh, let me actually do this so it's visible on the stream. There we go. Overwrite policy equals always. Yes. Let's touch. I've actually made another PR to fix this annoying thing. Up, there we go. Which I think has also been merged into... It's not called Lexa, it's called Scan. Wait, it's building... Yeah, 3.5.2, that's correct, yeah. Okay, so now the version of Alex, if I run this, we're back to a version pre-patch. So if I compile this small Alex file, and I guess, I'm sorry if for people watching the stream after the fact, you'll get the explanation twice. I guess you can skip 10 minutes ahead. If I run with those two things and I compile this, if I run Alex of this file and run Haskell the result, you'll notice that in the case of B, B, C, where we should be getting left B, left B, left C, we get right ABC. We are matching ABC despite the fact that this was not ABC. And if we look at the info for this, if I run Alex minus I of Alex0.x, and I look at the generated info file, we have here the state machine that Alex is using under the hood. So state 0 is our starting state. And when we find A, we go to state 2. If we find a B, we go to state 1. If we find a C, we go to state 1. State 1 is just we accept this current thing we're passing with action 0, which is the left constructor. And if we go to state 2, which is the one when we have match in A, either we accept, and again, Alex will take the longest match, so if that's the longest match, that's the one we take. Otherwise, if we find a B, we can continue to state 4, and here, if we find a C, we can continue to state 3, where we have the other accept for the other action, in this case, write ABC. The thing is, there's a minimizer that runs, which is this thing here, and it attempts to merge states that it considers equivalent. And states that are equivalent are not just that they have the same accept, the same outwards transitions, but they are basically arrived at through similar, like there is no input that distinguishes arriving at that state, basically. So here in this case, there should not be any states to merge. But however, we notice that there is no longer any state 4. We are down to 4 states from 5 because 2 states have been considered equivalent by the minimizer and have been merged. And now if we look at the state machine, state 0, whether we find an A, a B, or a C, we go to state 1. State 1 will accept the thing if there is no longer match. But from state 1, we can accept B and go to 3, accept C and go to 3, and do an accept 1. So ABC, BBC, CBC will all 3 be accepted as ABC. Because those 2 states, 1 and 2, got merged. And the bug was... do I still have it open? I don't see... No, I do have it open still. Here in this file, which is the minimizer thing in Alex, there's this big comment about the Hopcroft's algorithm for DFA minimization, which, again, as it says explicitly there, is copy-pasted from Wikipedia. And those 2 lines are wrong. And I don't know if the person who copied the thing from Wikipedia made that mistake, or if Wikipedia was wrong. But given that the French version of Wikipedia has some weird stuff in its declaration of the algorithm, like it makes references to stuff that hasn't been defined, I suspect that the pseudocode on Wikipedia was wrong. And what it does is basically, it starts with an incomplete, when it runs the code of like, okay, here's a set of all, basically the 2 lists we maintain are sets of states. And each set of states starts too big and contains states that should be different but are considered equivalent at first. And what the algorithm does is it segments those sets until there's no segmentation possible, and we end up with a long list of sets of states. Most of them only contain 1 state, but if 2 states are in the same set, then that means at no point we have managed to separate them, therefore they are equivalent. The problem is, since the second list that we're using as our cue to like try to segment the other sets of states does not contain all of them at first, if one specific set is necessary to be able to separate one of the other ones, and it never appears in our waiting queue, then we might be not splitting a set properly and return a set that contains states that should not be together but are together. And that's exactly what was happening. The trick is, since the algorithm was still mostly correct, it needed, for the bug to arise, it needed the order of the states in the original set of rules to be very, very specific. And for like, basically it needed to have a thing where at some point we split a set of 2 states into 2 individual states, because one of them goes into one queue, the other goes into the other one, and the one that didn't go in the waiting queue therefore never gets used for then trying to separate other states. Like, it was tricky to debug, but the gist of this was those starting states were wrong. So my patch was basically, I rewrote a few things, but my patch was just fixing the starting states of the thing. And the fun part is, I was mentioning earlier, there was a patch a year and change ago for like optimization purposes that changed a lot of things in this file. The bug was already there before, because again, the bug is from like 2011, I think. And the way to get the bug to show up in the pre-optimization version is to switch the order of the rules, because that changes the order of the states in the input set, and that is enough to make the bug show up. So yeah, that was a lot of fun, and the patch has landed, and Alex has been released with the patch on Saturday or Sunday, I think. So yeah, and now I'm back to working since we're done with. We are done with the thing we were doing last Tuesday before we got interrupted by this, which was doing tests for the AST and the parser and the pretty printer. I'm back to working on the compiler. And since I have not prepared anything, because again, this Alex bug has occupied my spare time for the last week, I'm doing something a bit easy this evening. I'm making some progress on the other end of things, the bytecode and image generation, which this phase I've been calling the linker, because it's kind of a linking phase. We have the bytecode for each function, and we need to assign a unique address to each of them. Because if I look at this example program, which is the one that is in the logo of the project, each vertical strip is a function, and we are going to have basically an intermediate step between the AR and the image generation, which is, okay, give us some bytecode, which is the list of instructions, and we're going to need to to assign a unique address to each function and to each entrance within the function. So return address after a function call, or address for a branch or a go-to, that kind of stuff. And then at the end, so we gonna at first have a list of instructions in the bytecode, which take as an argument the name of the place it's supposed to jump, and we're doing this linking phase in which we put them in a specific order, and as a result, we can assign numeric addresses for each place, because this thing here at the top of the screen is basically an addressing thing where we push a value at the top of the stack, and this strip here, basically, if it's less than 2, redirects that direction, otherwise does -2 and continue here, so that basically it points the execution to the correct address. So we were doing the linking stuff. So here, what this is going to be, so the interesting thing is, since functions can be mutually recursive, it is possible for a function A to need to know the address of a function B, and for a function B to need to know the address of a function A. I don't want to do 2 traversals, so what I'm going to attempt to do is use laziness, and as a result, basically have each function have the address it's pointing to be a lookup in a hash map, and that hash map being constructed as I traverse the function. But since it's going to be lazy, as long as I don't need to know the addresses, the lookup is not going to be performed, which means it's not going to be performed until the hash map is constructed. Therefore, it's going to be fine for mutually recursive functions to call the hash map even if the next function hasn't been processed yet. So this is going to be just going to be an eval state t or something like this, or just an eval state. Flip eval state of the initial state, whichever it might be. And what we're going to do is we are going to be first visiting the main function. And then we're going to do a sequence of instructions in our monad, which is going to be, so sequence takes a list of monadic actions, returns a monadic list of actions. So here we're going to create a list of actions to perform, and that list of actions to perform is going to be for, I guess I should do, no, I guess I can, no, let's do it here. Let's do it here. This is going to be functions main, and I'm gonna need import data hash map strict qualified as M. here I was thinking earlier about the fact I think I'm gonna make the assumption that this data here is well formed because none of it at this point will depend on user input. When we reach that phase of the compiler, we will be at a point where we've already done all of the type checking, name checking, lowering into the AR, generating the byte code. So at this point, all user errors should have been handled, which means if we get something that is not correctly formed here, it's our fault. We did something wrong. It's an internal compiler error. Therefore, I don't think there is a point in trying to like surface errors properly. We can just flat out panic there because like that's an internal compiler error. So here, for instance, I'm just gonna assume that like, yes, there is, if we're saying that the name of this function here is this, we're gonna assume it's part of the functions here. And if it's not, something has really gone wrong. And it should have been checked earlier, basically. So what we're going to do is for each name, and instructions in the list of pairs in this hash map, we are going to be visiting name instructions. Actually, we don't want to do a sequence here. We want to do a regular thing because that's going to give us a monadic list of the result of this. And I guess visit gives us our instruction pointer. Yes. And therefore here that gives us the list of all the functions that appear in our program. So this is going to be... How do we name this? Start, I guess. This is going to be all of the others. And the result of this is going to be start at the beginning of others. And the order matters because we're going to put them like side by side in the image. Do I want to store more information about each function? I probably want, actually, to store more. I think for each function, I want to store... I want to know the number of entrances that are in each of them, because I will need to know that to generate this strip here. Because what I'm doing here is basically, well, if the address we're going to is less than 2 or less than 3, depending on how I want to implement it, then I need to go to the right here to go to one of those, and otherwise I need to do -2 to it and just continue afterwards to the next strip. So I will need to know for each function when I'm generating this strip at the top how many entrances are in it. So I think I want to have that as part of my written here. Okay. Now, this link function is going to, I think, be our only expert. What do we do when we visit something? When we visit something, we have the name of the function. I guess we need that. Do we actually need the name of the function? I guess it doesn't hurt to have it, just in case we need to do some panic and... No, I think we don't actually need it. So I think I could just replace this like this, and this with LMs and just the instructions. So what we get here is a list of instruction with name of functions to call, and the result of this is gonna be the linking monad, so linker M, let's say, and the result of which is gonna be this tuple of int and instruction pointer. And I guess visit is gonna be basically just a traverse, or will there need to be something more? We'll see. For now, let's define what this linker M thing is. it is a state monad in which we're carrying some state, which we're going to call linker state, I suppose. And that's basically it. What do we need to carry around in our linker state? We are going to need to carry the current address, which is basically like the next value we can, the next available integer for an address that we can assign. So that's an int. And how do we call the mapping from names to address? Oh, wait, I'm wrong about something. This is not enough. Let me think. Because I think the problem here is the assumption here is like all of those addresses are just, in a case of a function call, the only thing we care about is like the address I'm recalling, the return address is just the next entrance in the current function, whose index we're going to determine during the linking phase. But that's not true for the branch and the goto instructions. Those are going to some arbitrary place within the current function. And that means I need to know at that time what that address is. Therefore, that address must be different per... Which is fine. I don't think it changes anything for what we've written so far for the linker. It means basically when I have something like, do I have an example here? I think this one actually branches to something like locally. Sorry, no, it doesn't. It's a go-to, I think, actually. It's a branch go-to. We could envision optimizations there actually, but maybe later. But like if we have a branch that takes it is a while and just goes to the same, like within the same function, it would need to know that it's going not to the entrance of the function, but to some other place in the function. So it needs to be able to distinguish them. So that means I need the entrance to also have an address. It needs to know what it is called, which I guess makes it a tiny bit easier. I don't have to worry about like, yeah, the entrance to a thing is always 0 of that function. I'm just gonna trust the assembler to have mangled the names in such a way that this is always correct. Basically, I'm just gonna make this here because goto and branch are local within the function. Call is going to be calling another function and therefore having to manage the stack there. Return, likewise, pop things go back to... Return is just an unconditional exit, basically. And branch is basically just a... No, branch is the one we do a switch. It's different. It's goto that's basically a push address return. Yeah, it's fine. Okay. So with that in mind, this is going to make our job here a tiny bit easier and push some work back to the assembler that we haven't written yet. That's fine. So how do we call the mapping? Addresses, I guess? Dictionary? The phone book? I don't know. Addresses. It's good enough. So this is gonna be a lazy hash map. I think a strict hash map is strict in its keys, not its spine necessarily. Let me check that. What are the strictness guarantees? It doesn't seem to say. The whole strictness properties thing is just this declaration. Yeah, I'm not sure what the. We can try. It's gonna be fairly easy. I think it's just gonna be strict, as long as it's not strict in. I think it's even if it's strict. Actually, I think it's gonna be fine, because what matters is for the lookups to be lazy. That's gonna be enough. So it's gonna be a lazy. Keys and values. Thank you. So key arguments are evaluated to weak head normal form. Keys and values are evaluated to weak head normal form before they're stored in the map. Okay, so the spine might not be. It depends, but I think it's fine. Yeah, if I will go to this version, let's see. Yep, thank you. I was not on the up-to-date version of the documentation. Yeah, okay, that means I think it's fine if the map is lazy because if the map is strict because the values in it are gonna be known at time of insertion. What I think matters is for the lookup expressions to be lazy because they need to be done at a later stage when the map has been built. So I think it's fine for the map to be strict as long as the lookups themselves are lazy. So I think I might not even need the state itself to be lazy. I think it's fine. But anyway, this is going to be a map from name to pointer, basically, as in the addresses of the different places that we encounter. Okay. I guess our initial state is going to be a linker state. And here's the thing, I think I want to use base 1 for addresses, just because it makes it a tiny bit easier to deal with this strip here. Because here, having to say it's less than 2, um, the only operation is greater, so I would have to say 2 is greater than. I think that works. I think there was a reason why saying 1 was easier. It was just because I didn't have to do O equals or something. Let me think about this. How does the greater instruction works in Pete? Let me zoom this on the stream actually. It's a strict greater. Okay. So here I want to continue. I want to continue if the value is greater than. Yeah, I guess if I'm just. If the second top value is greater than the top value. So it's easy if there are two entrances and there are 1 and 2 saying, okay, I push 2, I do a greater, and then I continue if it's true, is easier than trying to do flipping order of arguments and trying to do minus ones and stuff. So I think using a 1 address as the base is a lot easier. And also for the start of the program, I can just do 1 push. And since the size of a push depends on the size of the group of pixels, doing a 0 push is difficult. So I think using 1 as the start address is probably the easier, which means our linker state starts at 1 and our address map is empty. Okay, so what do we do when we visit instructions, what we're going to want to do is, excuse me, again, output the number of entrances in the given function, which is part of the result because we need to know that for the strip here at the top. There's 2 here, so we do a compare against 2, do -2. There's only 1 here, so we do compare against 1, do a -1. So we need to know that for each function. And transform the name into a pointer. So I think this is just... I think this is just a traverse of each instruction one by one. We don't need to assert anything about the shape of the functions because, again, we trust the output of the assembler. And what we do for each instruction, most of them are left unmodified. The only one that we modify are those. So let's do them one by one. So this is the entrance name. This is the go-to label, I guess. I mean, they're all names. The only place where it matters here is the order, and we have not decided. And I guess this is call name, and this is the return address, basically. This feels verbose. How do we call this? I guess return address is correct. Or backup. I don't know. I think return address is just a better name. Okay. So for each of those, what are we gonna need? I guess I can make a small helper function, which is name this thing. So assign of a given name is going to be the address is going to be the current address that we haven't used. We are gonna do ls current, which is our linker state current address, plus equal 1. And then we are gonna modify this mapping by doing an insert of that name is this address. Those shenanigans are gonna require make lenses of the linker state, which means I need to import control.lens and I need to have language template Haskell. So this creates lenses for those 2 fields, which means I can then use some of those operators to just make working with the state a bit easier. So yeah, assigning a name is we get the current, we upgrade the current in the state by 1, we change the mapping to be at this name is at this address, and we return just the address. So when we find an entrance with a given name, we assign that name, which gives us the int value, which is the pointer to, I guess I could call it pointer here as well. So we assign that name that gives us the value, and the result is just we apply the entrance constructor to the value that assign gave us. A goto to a given address is going to be the same thing. It's goto applied to assign of the name. Oh, wait, it's not aligning all that correctly. Branch is going to be the same thing. And call is going to be different. Call is going to be... That means, yeah, we need... Yeah, I think the order is correct. The name needs to be first. Wait, I'm wrong. This is wrong. Entrance is where I need an assign, but goto and branch, I don't need an assign. I'm not assigning a name. That's a lookup. I guess lookup is a name that's already in scope. Maybe not, actually. If it's in scope, I'll rename it. And for a call, it's going to be a lookup of the name. And then an assign of the return address. Okay. What is a lookup of a name? No, this isn't gonna work because I'm not... Because the value here in which I do the lookup, the expression I'm gonna use, it doesn't matter if it's lazy, it is going to be the current value of the hash map, which is gonna be changed by the next assign. So here, that doesn't work. I cannot do this thing. So I'm gonna have to do the thing that is even more complicated. Do I want to do this? I kind of do because it's fun, but it's gonna be a nightmare to debug if I get it wrong. I think I want to do some circular programming. Let's do that. So here I'm going to have the addresses, which is going to be my hash map of the thing. I'm going to have the register, which is a simple list of name to pointer. When I do an assign, I'm going to modify the register instead. And what I'm going to do, I'm modifying it by putting a tuple at the beginning of the list. So I'm not touching the addresses there. And the lookup is going to be... I'm going to be using the addresses. And what I'm going to do on the address is a lookup of the name, which we assume is always going to succeed. Okay. That should be all of it. Any other instruction is left unmodified. Ah, no. Okay, this is wrong because we're not doing the int thing where we are counting the number of entrances. So I need to do something a tiny bit smarter than that. I guess I could do that at a later stage. I don't need to count that at this point. It would be useful to have. It would be useful to know. Since I'm already traversing the things, I could be increasing the... Because this is just basically a... this is just basically a count number of function call and entrances in the function, which is not that difficult to do after the fact. But since I don't... yeah, I guess I can do this part of this. So visit a function is going to be... Do I want to put that in the state, actually? Like, do I want to have in the state something that counts? That might be the easiest. Which means here I can set the address count, entrance count. What's the operator I want? Is it dot equal? I think it is dot equal. Say that's 0. And then I do this traverse on my instructions. I'm going to change this to be a do block for each of them whenever needed. Losing the vertical alignment, but that's fine. Because here for the entrance, I'm going to need to increase ls entrance count by 1. Goto does not. Branch does not. And call does. Okay. Which means here at the end, an instruction just returns a pure instruction. We don't do anything. And at the end here, I can return. I can get. And I can return this total count and the result. There we go. Okay, so here is the trick. That is a tiny bit ugly, but very fun. And it's going to be a tiny bit annoying to debug if I get it wrong. Here, I'm going to be doing something. I'm going to rename this. Let me remove this altogether. This is going to be the go function that we're going to be calling. And here, I'm going to be doing... When I do a run state of go with the initial state, which contains now a few more things, current is 1, addresses is empty, register is an empty list, entrance count is 0. When I run this, I will get a tuple of my value of my result, and the state at the end of my go function, which is gonna be a linker state with some address count I don't care about, the addresses, and 2 other things I don't care about. Which means I'm gonna rename this final state. I'm gonna change initial state here to take the hash map and it puts it as a second argument. So addresses. Here, what we're gonna do is the initial state contains the addresses of the final state. And here our result is result. And this can work as long as creating the addresses never requires, wait, I'm wrong actually, this is wrong. This is gonna be a map from list of the register of the final state. There we go. So while we are processing this thing, we are creating this register, which is our list of name pointer. When we are done, we are creating a hash map from this list of pairs, but we are lazily giving it to the state itself at first. And that's fine as long as nothing needs to evaluate it before this is finished. And as a result, here the lookups can do this lookup into the lazily constructed hash map, and that should be fine. That should be fine. I don't think I will need monad fix or anything complicated or any caching here because I don't need to go process a function. They're all gonna be processed in order. Yeah, I think it should work. I think it is important that we keep a lazy state for this as a result. But I think the hash map doesn't need to be lazy because we are constructing it once when everything else has been, so I think it's fine. Okay. This should be all of it. Let's try to see if it compiles, and then let's try to see if it works. Yes, I need... What have I used as a convention for... If I look at my AST... Okay, the imports... I don't like this. I think I'm gonna do this where the imports of the current project are grouped after the imports of... So here I need the bytecode. Initial state does not compile. It's because there's a typo. Initial state. Or is it because... No, it's because I have the make lenses here. I need to have it last. Because the order of declarations in a file, in the Haskell file, doesn't matter until it does. And template Haskell is one of the things that makes the order matter. So I will put my lens declarations at the end so that it doesn't matter otherwise. But since they're declared here, since I want to use them in the functions, I might need to move... This is annoying. I'm gonna need to move this here. Because again, suddenly the order of declarations matters because of template Haskell. So I think I can probably... No, I need... So I'm gonna have to do this. I don't like to do this, but I have to declare them in this order. Okay. Text with int. Yes, I cannot just forward the instruction because this instruction is of type instruction with name, and I need an instruction pointer, so I'm going to need to write the full case here. So here, let's align this properly. Actually, let's do it with this. I want a group of non-spaces star followed by everything until the end of the line, basically. Oh, wait, this is matching the new line. That's wrong. So I want to skip all of the spaces, and I want a group which is none of the spaces plus, and then followed by a bunch of things, and followed by non \n. That work? That might work. and I want to replace this. Oh, actually, I need to keep the spaces. So this is a bunch of spaces followed by, wait, okay. This is a bunch of spaces followed by a bunch of, followed by basically the rest of the line. There we go. And I'm going to do this, this, this. Okay. Now we can align this by the arrow. This doesn't exist anymore. So those are all going to be the same. And those do not exist. There we go. So I can realign this. Okay, and that should be all of the boring cases because we handled the interesting cases here. And those are all the instructions that need to be unwrapped and rewrapped for the type conversion. Okay, that should be all we need. Can match instruction pointer with int. Is it because result is the result of doing... It should be... Oh, of course. This is a list of instruction pointer. Which I think... Yes, okay. Oh, wait. I have it wrong here as well. What am I missing here? The initial state... Oh, because this is... No, wait, that seems correct. Run state of go, which is this thing, and I give it the initial state, which is... Oh, yes, of course. This is missing either a dollar here, or more parentheses. Okay, we're getting close. Pure visit instructions. Because this sequence, we are creating a list of monadic actions, so I need to put this thing into a list. Name shadowing, so assign is already a thing in lens, and lookup is already a thing in GHC list. Okay, so let's rename them instruction assign and instruction or name lookup and address assign. So this is address assign, name lookup, name lookup, name lookup, address assign. I think using a lazy state means this should be fine. I guess we just have to try. Wait. Oh, because I'm in the wrong folder, that's why. I was like, why is it installing GHC and why isn't it installing this version of GHC? That's because I did my stack GHCI in the wrong folder. There we go. So here we should have access to the link function. We do. So let's create a very, very basic function to try first. So we are going to want to try. We are going to have, let me import data hash map strict qualify. Well, yes, this one can be strict as m, and let's try to do a link. So our functions are going to be our first one is going to have an entrance named main0, and I don't know, pop add call fibo0, let's say. Out int terminate. And the second one, oh, those are, this is a hash map, so it needs to have the name. This is main. Actually, we don't, except for main, we don't really need, but yeah, we do the main lookup, so we need the name of the function in a hash map. This is the Fibonacci function, let's say, and its instructions are there's an entrance called Fibo0, and there is a branch between that goes to Fibo1, and there's an entrance Fibo1. Let's say something like that. And a return at the end. Okay, so that's our functions. Call is applied to too few arguments. Yes, because at the end of a call, we need to say where we're coming back. We're going to come back to main1, which is going to be right after here. This is entrance main1. Okay, so that's a function. What happens if we try to link our functions with main as our starting function? And we messed up. We have an infinite loop. So, what part of this needs to be made lazy for this to work? Possibly the hash map. Unexpected laziness. Oh, yes, of course. There we go. By making the hash map lazy, so I have the strict data extension enabled, which changes the way laziness works by default in Haskell, where instead of everything being lazy by default, all of my fields of my records are like if there was a strictness annotation to make them strict by default. I also have another extension enabled, which is any field for which the size of the data is the same size as a pointer or less gets inlined because they're strict anyway. Field that is strict and therefore evaluated when creating the structure, and the size is less than a pointer, just inline it and entirely remove the pointer, remove the indirection. Those extensions tend to be better in terms of performance. Function arguments are still lazy. Laziness is still there, but whenever we persist something to a record, evaluate the thing. This tends to be a better default. And we can always recuperate the laziness with the laziness annotation, like here. So here, when we create the address, we want this hash map to be lazy because we are creating it. We are creating it here at the top. So at this point, it needs to be lazy because it needs to be pointing to something that will not be available until later. So we make it lazy, and now this works. So here we have 3 for main, because entrance has 1. Oh, yes, I have the. This is technically incorrect, I suppose, but that's not the fault of the linking function. I have this call here, which will contain an entrance and then the entrance. Or do I decide Nah, I think it's easier to just have every call followed by its own entrance. I don't know. I don't know. Are there cases where I would like to have a function call not followed by an entrance back into the function because I know? No, I don't think there is. I think I always want to have. But do I want to separate? I think it's fine that way. Yeah, we can always decide later. But as a result, yes, there were one entrance, one call, one main, so 3 is correct. Main 0 is now 1. Call 500 is now 7. Why is it 7? Something is wrong. Because 500, its entrance is 4. So something is wrong here. And the call here is 7 for 500, which is wrong. And here there's another call, which is the one in the Fibonacci function. Wait, why is there a call there? Oh, I know what's wrong. Something I meant to do that I forgot. Here, we need the name instructions to list because we need to check that we are not processing a main twice, basically. There we go. That makes a lot more sense. So call 4 because the entrance of the second function is 4. The return address is 2. Okay. Then entrance 3, then entrance 4, branch 5, entrance 5. Okay. So that seems to be working. So that's our linker done. We'll probably want to write some tests for this at some point. I don't think it would be monstrous to just write some properties of this. What properties do we want to assert if we're doing something like this? I guess a property that we want to assert is we could check that every call has. I was going to say every call has a corresponding entrance, like that things map to one another. The big problem would be that I would need to generate arbitrary things using quick check that match. Like there is an entrance for each. There is an entrance for each. I'll think about it because I think we want to have some tests for this, but I don't know what shape they should take. Because I think we probably want some property tests, but I'm not sure exactly how to generate things with quick check that makes sense. I'll think about it for next time. But I guess we could start thinking about the assembly phase. Which is going to be taking the output of our linking phase. Which is this. And makes an image. Now, the thing I want to do with this, and I don't think I'm going to finish this evening, I think what I want to do is have a bunch of files that we're going to load at compile time that contain a pattern of colors that we're gonna interpret and like basically make small sub images and then create the image by pasting them wherever required, basically. So this is going to require a few things. First, this is going to require we are going to need to know about the Piètre colors. Are they called? Yeah, they're called light, name, and dark. Then we have yellow. Oops. Which is probably maybe the longest, so I can rearrange things based on it. Then we have green, I believe. Then cyan. Then we have blue. 5, and then we have magenta. Might be longer than yellow. From this, what are we going to need? We are going to need to know, for a given instruction, we are going to need to know how to encode for an instruction for a color, what's the next color we need, basically. So next color, given an instruction and a color, regardless of the type of address, give us the next color. Knowing that some instructions that we have in our enum type are not Piètre instructions, but blocks that we have that are special. And I think basically what we want to return in that case is what is our starting color, basically. Because in a bunch of places in the image, like here in the top left, or at the beginning of a function after the address block, or at the beginning of this, or at the beginning of this, we are free to start at any color, because again, it's the color transitions that like mark what is happening. So we just have to decide what we want our starting color to be, and all of the starts like will have the same color everywhere, which is neat. I think green is a pretty good starting color. So let's do that. I guess I could even change the starting color based on where we're starting. So if we ever decide that we don't like this, we can always... I guess I could make it return a maybe color and then let the color decide what the color decide what the color should be. But for now, I think it's fine to just say we always start at green or something like this, and we can refine later. So if I go back to our instructions, Or do I want to do it the other way around? I might want to do it with color first, actually. So this is the list of things we are gonna find. This is gonna be, I'm gonna call it name. Although at this point, it's probably gonna be an address instead. And basically, those are the special cases, and those are the base ones. And here's where we're going to need to encode the translation in terms of because it's not just a matter of like increasing an index in the thing of the color. It's a matter of doing a modulo 2 on the value, basically. And then doing I'm going to make a step function which, given a color and given an int, which is the number of steps in hue, and an int, which is the number of states in lightness, will give me a color. And a step for a color, hue, and light will be, so from enum, it's going to be something. Index is going to be from enum of the color, because color will have let me actually look at something. If I look at enum, is there a notion of the... No, there is not, but bounded might. Is it just min bound, max bound? It is min bound, max bound. So if I have color, which is red, green, blue, this, deriving enum bounded, if I do a from enum of the min bound, which is a color, that's 0, and max bound. So that tells me the maximum index. So I guess I could not hard code it. At the same time, I'm going to need to hard code a few other things, so maybe I don't need to do that. So here I get the index. And actually, it's going to tell me it's going to be a div mod 2. So we take the index in this thing, we do a divided by 3 and the modulo of this. So 0, 1, 2, 3, 4, 5. The division tells us if it's red, yellow, green, cyan, blue, magenta, or whatever else. And the modulo tells us if it's light, normal, or dark. Then the result of this is going to be color plus hue. I guess it's like this is. Let's name things. Start hue, start light. So it's going to be the start hue plus the difference in terms of hue. And this is going to be modulo 6. So if we are on magenta and we're moving 2, we get 7. Yeah, we get back to yellow. That's correct, yeah. And it's going to be plus modulo of start light plus diff light 3. I think that's correct. We need to test that. Okay. And with this, all of those are going to be the same. They're going to be step of the color by some values of hue and light. And now we can go back to this and have a look. A push is 0 hue, 1 light. A pop is 0 hue, 2 light. And I think they are in order. I think this is 1 hue, 0, 1, 2 in light. Add, subtract, multiply. Yep. Divide them out, not. Yep, so that's just 2. Greater pointer switch. Yep, that's 3. Duplicate roll in int. Yep. And in character, out number, out character. 5. Perfect. And this is always going to be 0, 1, 2, 0, 1, 2, 0, 1, 2, 0, 1, 2, 0, 1, 2. Okay. And here we have the other cases. Actually, those, the names don't matter. I can just remove them. And here we've said that for now, our starting color is always going to be green. Oh, actually, I am going to need to do here a 2 enum of this. Because I'm using the int value of the index. I compute the new index and I do a 2 enum. This is a partial function. This will panic if I get the index wrong. But hopefully I won't. Okay, that seems to compile. So if I do the next color after light blue and I'm doing a push of 3, it tells me dark yellow, which is wrong. Oh, yes, because I need to multiply this. This is 3 times this. Right? Oops. So if after a light blue, which is the same hue but 1 step darker for a push, we are indeed at blue. After a light blue, if we do a pop, dark blue, that's fine. And after a dark blue, if we do a pop, we stay in the same hue, but we should go back. So we should be 1, 2, so we should be back at blue. We're back at blue. Okay, so now it's showing that the lightness cycle is working within the same color. Let's try one step, zero light. One step in hue, one step in light is subtract. So if I do after a dark blue a subtract, I get light magenta. Is that correct? After dark blue, we've moved 1 and 1. We get light magenta. We should be getting red after light magenta. Yep, okay, perfect. And now if we try a out character from this, from light magenta, we should be moving 1, 2, 3, 4, 5. 1, 2, we should be getting a dark blue, I think. Yep, perfect. So that seems to be working as well. So I guess now we need to decide if we're doing this thing where we import templates that have I was thinking of using basically ASCII art for the templates, where like a character represents like space, represents transparency. There is no need to add anything there. Black and white are like B and W, something like this, or like maybe pound and dot or something like this, so that the structure is very visible. And then, but then I would need to have 17 different values for the colors. Or I guess I can use stuff like, I don't know, A to whatever, and maybe use characters for the other ones. And then I translate that to indices into. And the only thing is, then I have indices to apply to a start color, and I can just translate whatever thing. Yeah, I think that would work. Let's try to do that. This probably should be elsewhere, not directly in the assembly code. I'm gonna do the same thing where I think staging. What am I doing? Like we have for parsing, where I'm gonna create a folder, and this assembly thing will do the same thing as the parsing thing, which is just call things that are within the assembly folder. So first we're gonna make a color module, which is gonna get those functions. Oops. It's gonna get all of them. There we go. Then we can make a template file in which we're gonna do this translation thing. Do I want to deploy parsec for? Nah, that feels extremely overkill for what we're going to do, since it's just gonna be a matter of parsing. It's gonna be a matter of parsing extremely basic files. Yeah, it's gonna be very. Yeah, I think I could just like even make it using string is fine, because it's not even gonna it's even gonna be done at compile time anyway. So I can probably just do that as a string. Actually, is text traversable? It's probably not, right? Because traversable will require the thing to be a functor. Yeah. Is it an is list? It is an is list, so I can always convert some lines of text back into lists if I want to iterate over them, I guess. I'm just gonna do it on string for now. Performance at this point is extremely unlikely to be a concern, since again this is gonna be done at compile time. So parsing of a file is going to be, we're gonna have a raw string, which is the content. Read template, and it's gonna give us a list of lists. We probably want to do something smarter than this and immediately output an image rather than using lists as an intermediary representation. It's okay to iterate through lists, but creating more lists might not be great. But I don't know yet what image library I want to use. Maybe for the sake of testing, for now I'm going to do this, and I'm going to replace this afterwards into another type. So this is going to be, for now, it's going to be a maybe color, because either it's a transparent pixel that we don't want to overwrite and it's nothing, or it is the color we want to specify. And for do I want to specify at this point what the starting color is, or no, it's going to depend. The template will depend on what the previous color was. So the color needs to be agnostic. So it's a maybe int, it's the amount. It's the amount by which we need to increase the previous color. Yeah, I think that's what it is. That's not generic. That's not generic. That's a problem. Okay, I need to think. If I want to use a one character code for each color without hard coding colors, that means I need to have something that to each one character represents a combination of hue and light changes based on the previous one, which I guess is one letter per instruction. And I can use 0 as the special. I can use 0 as a way to say whatever the starting color is, and then associate a letter to each instruction. Yeah, that's probably fine. The question is what letter we want to associate to which instruction. So reading a template given some string s is going to be decomposing it into lines. And then for each map, for each line, map, translate, I guess. I can just even remove the S here. If we find space, we return nothing. If we find this, we return... We don't have black in our color, actually. We probably need to have black and white in our enum. What that means, however, is that this should never be called... This is going to be wrong if we ever try to step from black and white. And this is also always going to be wrong if we try to step from black and white. But it's not wrong in the way that it's going to crash. So that's fine, I think. It's just it's gonna be nonsensical if we call step and next color on black and white. I think I'm okay with that. So this is going to be just black. This is going to be just white. Then let's say 0 as the starting color, so whatever it ends up being. And this is going to be therefore a tuple of int of the steps to apply. Yeah, I think that's correct. I think that's correct. I guess we could just actually encode this as an instruction. Like it is a push compared to the previous one. Yeah, I guess we could encode it as an instruction. But that opens, like, which type leads to the fewer wrong representable states? Ints allow us to represent a bunch of completely absurd translation, but instructions opens us to having like entrance and other like weird things that are not supposed to be there. I think it's better to have int because we are going to be translating instructions into templates, and templates, if they contain instructions, we're going to require more translations. So I think we just want to have the raw ints and avoid the possibility of having recursive instructions that contain other instructions. So 0 is going to be just 0, 0. And now we need to define what characters we want to associate with each instructions. We have push and pop. Do we do like uppercase p, lowercase p or something? Like this is a push. And this is a pop. That's probably going to be confusing. I don't want to use plus and minus because I'm going to use that for addition, subtraction. I guess push and like delete basically with an X. Yeah, I guess that works. Okay, let's go back to instructions. So that's our list. Add is easy, it's going to be a plus, and that's just 1, 0. The only thing that annoys me here is that I'm encoding a translation from like instruction to offset a second time, which feels inelegant, but not the end of the world. Multiply is just 1, 2. Mod is going to be percent. Actually, I can probably copy from color. I can probably copy this list. Okay. And I can actually pre-fill this as being some character arrow. There we go. So after modulo, what do we have? We have not, that's easy, that's going to be this. Greater, that's going to be this. Pointer. Pointer, what do we do? Pointer is the one that rotates the instructions, so that's the one that gives us. But I probably don't want to use R because there's also roll, which I think I want to use R for. So pointer, the thing that rotates where we're going. I guess D for direction? Yeah, it's not the worst. Switch can be S. Well, no, D is probably going to be duplicate. I can use the caret for pointer, as in where the thing we are pointing to. Looks like kind of like an arrow enough, I suppose. Or I could use 9 for 90 degrees. Or slash? What one character conveys rotation the best? I think I like caret just fine. Then we have switch, which I think can be S, duplicate D, roll R, and then we have the four input output functions. For which I'm just gonna use lowercase, uppercase. I think those are rare enough. So input int, input char, output int, output char. There we go. And anything else is an error. I don't need printf for this. Okay. And I guess as a temporary thing to debug what we have, I could do something which is a render of a list of maybe int. That does an IO action. And prints something in the command line. Let's do that. So it's gonna be. I think we're gonna need to use a statement to keep track of the current color. That's fine. So this is gonna be an eval state t of go, with the starting color being green, let's say. And go, actually, I can already replace this. Let's just keep go for now. Go is traverse line of the template. Line is traverse row, column, traverse pixel of the line, and then lift IO of print a new line. Okay. And what is a pixel? And with a maybe thing, it's going to be a case here of If it's nothing, I'm gonna have a look at my Advent of Code library actually. So I do not remember how to do color in. Oh, that's ugly. We love this. Okay. Can I put this here? I'm gonna need text printf. I'm actually gonna need more than this. I'm gonna need. I probably have the state monad already, but I still probably need control monad state. I will need as well. What do I need? There's something else I needed, I think. Yes, I need control monad IO class to get the lift IO. Okay. So now this is going to be a helper function in this, and it's going to take RGB. Okay, there we go. So in the case of nothing, we're just going to just print a space. And in the case of just hue and light, what we're going to do is we're going to get the current color from our state monad. Oh wait, this doesn't work. Here I'm saying just black, just white. This doesn't work. I think this needs to be... And yeah, 0, 0 is wrong. Okay, so this needs to be a special type. It needs to be a small template pixel type that contains absolute, which is going to be containing an actual color, which is for black, or actually it's going to be black. Maybe I can remove black and white to the template and always hard code them here, because black and white are never going to show up in my images otherwise. They're always going to be in the templates. Nah, I think they need to be in the color. It's going to be easier. So it's actually either an absolute color or a relative int, or it's going to be a start color. Okay, so here I can rewrite this as being or transparent. I probably only need show here. Okay, so let's rewrite this. This is transparent. This is absolute black, absolute white. This... Oh, this is all wrong. I just realized I got everything wrong. So I need to keep this. I'm going to add one additional line, which is going to be a copy of this one. And everything here needs to be switched one up, I think. Wait, but I end up on 5.2. What have I missed? So 0 is gonna be start. This needs to be fixed like so. But I forgot one of them. So push, pop, add, subtract, multiply. I forgot divide. So I can copy that, print it here, delete this, and divide. Divide is 2, 0. And then we have everything from 0, 1, 0, 2, 1, 1, 1, 2, 2, 2, 3, 3, 3, 4, 4, 4. Okay, there we go. So I think I had just forgotten divide. So now this is start, and all of those are no longer just, they are relative. Okay. Go back here. So we get the current color from the state, and then we can do a case of that pixel, and then all of those things are different now. I need to figure out how to print. I guess I will hard code here the absolute ones at the end. So if we get transparent, we do exactly that. I guess here I can just do a lift IO of the whole thing because it doesn't need to be in my statement anymore. Or does it? It does, because some of them will increase the current color. Transparent does that. Start just prints the start color again. So I will need to have some kind of way of choosing for a color. The start color is going to be green, as decided earlier. And print color is gonna be a case of, and I can go back to color and other color, this one. Get that big enum here. Oops, I'm wrong. I meant to do this. Yeah, I guess. I probably should have inserted. That's fine. Let's do it now. Now I can align this properly. It doesn't want to align properly, that's fine. Okay. Okay. Now, this is always going to be a actually just going to be a lift IO of a printf followed by 3 RGB values. The printf is going to be this nonsense. Which I guess I could just, yeah. I can keep this, and this is just... Actually, I think I want to copy the other one. I think I want to copy this one. And print a space. There we go. This makes no sense. Let's remove that. And here this is now print color and with 3 arguments. Okay. And now I need to remember what the colors here. FFC0. Okay. So light red is FF here and C0 for the others. Red is FF. So it's FF for all of red and for... Wait, no, it's C0 here. It's FF, FF here and also here. And then green as well. And not for dark green, however. For cyan, FF, FF, but also in the blue. Then light blue, dark blue. And then finally light magenta and magenta with the red. And black is 0, 0, 0. And white is FF, FF, FF. And I think for transparent, I'm just going to actually print a dot to differentiate. Okay. Okay, so for light, red, F0, is correct. For red, it's F0, 0. For dark red, it's C0, 0, 0. Light yellow, FF0 is correct. Then it's FF0, and then it is C0, C0, 0. Light green, that's correct. Green is zeros there and there. Light cyan is C0 here, 0 here, 0 here. Why is dark? Yes, C0, 0, that's correct. Light blue. Blue is 0, 0, and dark blue is also 0, 0. Magenta is 0, 0. Okay, that should be fine. This is debug code anyway, so it's not that important, but it should be fine. And last but not least, we need to finish what we're doing here. So we've handled transparent start, and we need to handle absolute and relative. Okay. So if we have an absolute color, then we do a lift IO of print color of that color. And finally, if we have a relative adjustment of... I guess it's a constructor, I don't need to have a double, it can just be int, int. Okay. So I have relative hue and lightness. In which case I need 2. And I can probably then go back to doing the thing I was doing of this is a backslash case. I get the current color from the start, which was obtained through get. And I will obtain the new color by doing a step of that current with H and L. I'll put the new color back in the state, and I will lift IO, print color, new color. Okay. And this needs to be there as well, yes. This should be enough for us to try parsing a template and printing it as a debug. This requires color is actually in stages. As what do you call it? Assembly, yeah. And this needs, of course, where is the previous assembly file here? It needs the bytecode. Control net state. Oh, apparently I already export stuff from control net state in my prelude. Print color has more. Yes. This is not print color, this is pixel. Wait. No, this is. This is going to be display. And this is going to be display. With this being print color. Wait. Yes. And finally, I have something here where I do a traverse, but it needs to be a traverse underscore because I am discarding the result. And this is no longer a list of maybe tuple of int. This is a template pixel. Okay. Yes, here it doesn't know what the type of the arguments are, so I need to specify explicitly those are ints. I could make them word 8 actually, but int is fine. I could, I guess, remove all of those lift IOs. Plus display start color is not correct. Lift IO here isn't required. So I could probably just do a lift IO here. And that's in for some monad IO M. That's M in this. There we go. And now this should be fine. Okay, so I have some inconsistency here where some of those functions are returning IO and some of those are returning something in the underlying monad, which means I have something here that's unclear. So here line should be returning something in the underlying, in the state monad on top of IO because it's doing a lift IO for the print, which means I need to make sure that pixel itself is returning something. So here we're doing a lift IO for print and we're calling display. So I need to make sure that display returns something which is in our monad. Here I'm doing a lift IO display. That's what's wrong. There we go. Okay, this compiles. I don't know how GHCI handles printing color. Worst case, I'm going to reuse another program for something else. I won't stack GHCI. So if we have a block which is, I don't know, a line of walls followed by inner wall 0, 0, and the end of the thing, followed by wall dot dot for white, followed by we restart at the 0 color, then we do a push, which is the P letter, then we do I don't know, a division. That would not work in an actual program, but that should be fine enough. So that's a string. If I try to read template of that string, that works. Start, that seems to be working, perfect. And now if I do a, how is it called? Render terminal of read template of S. Okay, that seems to be working. Except black is not rendered properly, so maybe for black I should use something else. Yeah, I guess black and white could still be. Maybe this should take as an argument the string. And here I'm gonna print. Oops. A space every time, but for black and white, I'm just gonna print those characters. Therefore, transparent can be just this. And here, their background is gonna be. Actually, I can do that. Yeah, okay. Display new color. What is wrong? Yes, display new color. Yes, here this is wrong. This is also taking a string. And therefore, there we go. So now if I try this again, okay, so white is rendered like this. I don't know what the lines are. There's something wrong about the lines. Oh yes, because I'm doing a print string followed by a new line of a new line. So I just need to do this. Okay, so now we have the walls rendered as the hash sign. White is rendered normally. Transparency would be rendered as transparency. But we do have a setting color. We have a setting color. We have here, this is... What did I do? I did... Oh, this is wrong. This is completely wrong. I think having the relative thing in the render being proportional to the starting color makes no sense. Like to the current color, I think it should all be proportional to the starting color, because otherwise I cannot express groups of pixels. So this is wrong, and this is not how we should be doing templates. Which means I can revise all of this. This is just go. There's no need for the statement at all. This is just that. And start color is green. That is correct. Line is this. Except, yeah, this is all of that is correct. I can remove all calls to lift IO because this is just going to be in IO now. And when it's relative, it's going to be relative to the start color. So now after doing start color green, we do a push, which is one darker than the starting color. And then we do a divide compared to the starting color. Ah, that's the downside of using... That's the downside of using names for colors which are... Ah. Because it means I'm going to be using in my template something like divide, but not to mean actual divide, but to mean the same amount of steps from the start color as a divide, which is going to be very, very confusing. Because now this is a divide which is blue compared to the starting green. So it's a dark blue, I think, because divide is two steps in hue, no change in lightness. So it is indeed blue, yeah. I'll have to think about it. I'll have to think about whether I want to change this to actually be like another name for those that is not impacted, like just maybe like letters from A to something rather than trying to give them... Maybe that would make more sense, yeah. I'll think about it. I think I'm gonna stop here for this evening though, because that's progress. Next time we can do reading the template file at compile time, which means having files included at compile time, which is always fun. And we can start, I'll look into which image library I want to use, and we can start composing images to make Piètre programs out of bytecode. And yeah, it's gonna be fun. But yeah, I'm gonna stop for this evening. I'll commit all of this because I haven't committed anything in a week because I was again too busy with the Alex bug. And yeah, thank you for tuning. Thank you for tuning in, and I'll see you all on Thursday. I haven't updated the calendar, but I will be streaming on Thursday. So yeah, see you all then.